So here I'm going to solve problem number 431, and it has a chair sitting on the floor. Obviously it's not falling through the floor, it's just kind of sitting there. And you come along and you exert a force on that chair of 40 newtons at an angle of 37 degrees. And it says draw a clearly labeled free body diagram for the chair. So I'm going to do that right down here. This point here is going to represent my chair, and a free body diagram is going to represent all of the forces that are acting on a body, in this case the chair. So the first thing that we can put on this chair is going to be my force of 40 newtons acting at an angle of 37 degrees. I also know that the chair has some mass. That mass is going to mean straight down I'm going to have a force due to its weight, which is going to be the object's mass multiplied by gravity. I've also said that the chair is not going through the floor, so it's being supported by the floor. It has some normal force that's doing that. And last but not least, this is not a frictionless problem, so friction is going to exist, and the friction is going to be in the opposite direction as the force, and it also has to be parallel to the surface. So here I have my frictional force, and what I'm going to do is so this is part A, and now I'm going to use this diagram to calculate the normal force that the floor exerts on the chair. Now to do that, I need to first break up the force that I'm putting on this chair into the x and y directions, and that's going to simply make it easier for me to sum all the forces in the various directions if I need to do that, which I do. So over here I have my force in the x direction, and that's going to be 40 multiplied by the cosine of 37, and in the y direction it's going to be 40 multiplied by the sine of 37. Hope everyone is now comfortable with me doing that without writing it out explicitly. And it says, now I want you to calculate the normal force. I know in the up-down direction my chair is not accelerating. So what I can do is I can write Newton's second law. The sum of the forces in the y direction is equal to the mass times the acceleration in the y, which is going to be equal to 0 because the acceleration is equal to 0 here. And I look at all the forces in the y direction. In the positive direction I have the normal force, and in the negative direction I have the y component of the force that I'm pushing on the chair with, as well as the weight of the chair. So now I can go ahead and rearrange this guy to say that the normal force must be equal to the force that you apply to the chair in the y direction plus mass times gravity. So you go ahead and you write that out. 40 sine of 37 plus the mass is 12 kilograms, and gravity is 9.8 meters per second squared. I've already taken the negative into account when I drew the gravity in the negative direction. So you punch that into your calculator and you come out with 142 newtons. Now I'm going to take this problem a little bit further and say, what is the acceleration of the chair if mu sub k, the coefficient of kinetic friction, is 0.1? I didn't say what type of friction I had in the last one, I just said that it had some friction. Now I'm telling you, okay, the chair is sliding. Now let's calculate an acceleration. So now we go back and we want to say, what are all the forces acting in the x direction? And I'm telling you the chair is going to be accelerating, so it's going to be the mass times the acceleration in the x direction. And for this guy, we're going to have the force of friction in the negative direction, telling you that it's kinetic friction. And then we're going to have my force in the x direction right there. So the acceleration of the chair is going to be equal to negative f sub k plus the force you're applying there, divided by the mass. The frictional force is going to be the coefficient of kinetic friction multiplied by the normal force. Now, we calculated that in the last part. Don't forget my negative sign, divided by the mass. So now I know what all these guys are. I'm going to have negative 0.1 multiplied by the normal force, 142 newtons, plus 40 cosine of the angle, all of this guy right here divided by 12. Then you punch that into your calculator and you come out with 0.82 meters per second squared. Here we're going to solve problem 454. You might want to pause for a second and read the problem real quick. The first thing it asks you to do is draw the free body diagrams for all of the blocks. So here I'm going to have my 6 kilogram block, and I know that that guy is going to have the upward force of 200 newtons right here, and it's going to have its weight, its mass 6 multiplied by gravity in the downwards direction, and it's also going to have some tension at the top of the rope. That's where my little subscript T there means, tension at the top of the rope. Because the rope has some mass, the tension at the top of the rope is not going to be the same as the tension in the bottom of the rope. So now I'll go ahead and I'll draw my rope. Just draw a little point right here. This is going to be my rope. In the upwards direction, it's going to have the tension at the top of the rope. It's going to have its mass times gravity in the downwards direction, and it's also going to have some tension at the bottom of the rope due to the 5 kilogram guy pulling on it. Last, let me draw my 5 kilogram block. I'm just going to draw a 5 right here so we know what we're talking about. And that's going to be pulled upwards by the tension in the bottom of the rope, and it's going to have strictly just its weight. It's mass 5 multiplied by gravity, pulling it downwards. So, going ahead, I'll draw my free body diagrams. Now it asks for what is the acceleration of the system. And we know that since all of these guys are connected, they're all going to have the same acceleration. The 6 kilogram block, the 5 kilogram block, and the 4 kilogram block are all going to have the same acceleration. So what I can do is I can say I'm going to draw a box around this guy, and I'm going to say this is now my system. So now I need to draw the free body diagram for my system. This system is going to have the mass of the system multiplied by gravity in the downwards direction, and it's being pulled by a force which is going to be 200 newtons. Now I can write Newton's second law and say for the system the sum of the forces, in this case it's in the y direction, is going to be equal to the mass of the system times the acceleration of the system. So I'm going to do that more explicitly over here. Sum of the forces in the y is equal to the mass of the system times the acceleration of the system. And in the upwards direction, I'm going to have my force. In the downwards direction, I'm going to have the mass of the system multiplied by gravity. So what I can do is I can say, well, I know that the mass of the system is going to be the mass of all three of these guys added together. 5 plus 4 plus 6. That's equal to 15 kilograms. And I'm solving for the acceleration of the system. So I can write the acceleration of the system to be equal to the force minus mass of the system multiplied by gravity, quantity divided by the mass of the system. So that's going to be 200 minus 15 times 9.8. Divide all that guy by 15, and we come up with acceleration of 3.53 meters per second squared. So to calculate the tension at the top of the heavy rope, I can use the fact that I know that the acceleration of each of these blocks is going to be the acceleration of the system. And let's take a look at the free body diagram of my topmost block. I know in the downwards direction I have the mass times gravity, and I have the tension at the top of the rope. That's the quantity I'm looking for. I have my force in the upwards direction. So for this guy, I can say the sum of the forces is going to be equal to the mass of 6 multiplied by the acceleration, which I found in the previous part of this problem. And that's going to be equal to the force in the upwards direction, I know what that is, minus the tension at the top of the rope, minus the mass of 6 multiplied by gravity. So I can write the tension at the top of the rope to be equal to the force minus the mass of 6 times gravity minus the mass of 6 times the acceleration of the 6 kilogram block. So that's going to be 200 minus 6 times 9.8 minus 6 times 3.53. So the tension at the top of the rope is going to be 120 newtons. Now we can take this a step further than what the problem asks you to do, and I can say, well, what would the tension at the bottom of the rope be? So to solve for this guy right here, I would take a look next at my rope and say, let me write the sum of the forces on the rope, and that's going to be the mass of the rope multiplied by the acceleration of the system. And I'm going to have now the tension at the top of the rope going upwards minus the mass of the rope minus the tension at the bottom of the rope. And I can then say that the tension at the bottom of the rope must be equal to the tension at the top of the rope minus the mass of the rope multiplied by the acceleration. I forgot my gravity term right here. Minus the mass of the rope multiplied by gravity. Now, I know what that is. I know what that is. This is 3.53. I know what that is, and I know what that is. So I can go ahead and I can plug all those guys in and come out with 79.3 newtons. And you ask yourself, well, does this make sense? Yes, it does make sense, because at the top of the rope we have 120 newtons. Down here at the bottom of the rope we have less tension in the rope, because up here we have the 4 kilogram mass pulling on it and the 5 kilogram mass pulling on it. Down here we only have the 5 kilogram mass pulling on it.